Okay, let's get started. So before we get started, are there any questions from last time? Yes.
I have a question as to what happens when you induce two pulses in succession, and this, I think, sort of ties to the homework.
Sure.
Which is, if you apply a pi-half pulse, which takes you perpendicular to to your z axis, you start to recover and process, and then you apply another pulse of pi. Does that take you back to pi as in aligned with the z-axis again, or does that rotation continue all the way as a 180 rotation?
Okay.
Sort of, if that makes sense.
Yeah, so we'll talk about that. We'll go over that problem in a few slides. But the basic idea is, so if I have magnetization like this, and I tip it with a 90-degree pulse, right? So at that instant, what is m sub z of 0? What is m sub z? It's 0, right? There's no z component, right? So then this is going to process, and then it's going to die away with some t2, right? So then at some point, mxy is equal to 0, right? M sub z starts growing back, and then if I come along later and tip it with a 180, it just flips it over like that.
So it would pass the axis. So the pi pulse is just a rotation of 180 degrees.
Yeah, so anytime, right, a flip angle just rotates it by however many degrees.
Okay.
So a 90 degree rotates wherever the magnetization is by 90 degrees, 180 just rotates it 180. If it's here, it would rotate it this way.
And so does the recovery of that occur the shortest path back to being aligned to the magnetic field, or will we see the rotation the other way again?
Yeah, actually, if it's, okay, so the recovery is always just back like this.
Okay.
But the flipping goes like this. So if I flip from here to 180, at any point if I stop, the magnetization will be there. Okay? So flipping is rotation of magnetization, but relaxation, longitudinal, just goes back here. Just regrows.
And the shortest path to get back to equilibrium.
Yeah, because basically, it's basically just the longitudinal relaxation is just how many spins are more aligned. So that's just going to just grow back like that. Okay, any other questions? Okay. So we may or may not return the midterms. Do you know if Liz is coming today?
Yeah, he should be a little bit.
Okay, so if she has the scores recorded, then we'll return the quiz 2s at the end of class. If I forget, someone just remind me. Okay. Quiz 1, sorry, quiz 1. Okay, so let's start on, if there's no more questions, let's start on today's lecture. So today we're going to review a little bit some of the concepts, and then we're going to mostly focus on encoding with gradients. We'll work up to the MRI signal equation, and then we'll get into k-space trajectories and pulse sequences. All right. So just to remind you where we're at, we've already talked about using the large magnet to polarize. That's where we get the magnetization. We've talked about excitation, tipping the magnetization away from the equilibrium. And so today we're going to review, last time we talked a little bit about encoding, so we'll review that today. Basically, we use the gradients to impose spatial patterns onto the spins. All right? And each spatial pattern corresponds to a place in Fourier space. Right? And then we use the RF coil to integrate all the spins, and that's forming the integration part of the Fourier Transform operation. So we went over the Bloch Equation, which had 3 main components. One is the precession around the main magnetic field. Okay. There's also transverse relaxation, which is the decay of the transverse component, the mxy component. And there's also longitudinal relaxation, which is this regrowth of the m sub z. Right. And so very applicable to the homework problem that we're mentioning is that the governing equation for the recovery is this. So that's the differential equation that governs recovery, which we talked about last time. And this is the solution. Okay, so you're given the solution for wherever you start off, this is how m sub z will recover. Okay, so in that homework problem, all you need to do is use this equation in the right way. Okay. So for example, if I do saturation recovery, so saturation recovery means that corresponds to after a 90-degree flip angle. Okay, and that's assuming I'm starting from m sub 0. Okay, so by full magnetization, so I'm fully relaxed, so I have all of my magnetization is m sub 0. And there was I think there was a question, one of the TAs relayed to me, there was a question, what's the difference between m sub 0 and m sub z of 0? Okay, m naught is just the equilibrium magnetization. Okay, so that's just how much magnetization you get from that big magnet. That's the maximum amount of magnetization you ever have to deal with. Okay, m sub z of 0 is just how much of that magnetization is along the z component. So that could be anywhere from 0 to m sub naught, and it could even be minus m naught. Okay, so that is just the starting point of that m sub z component. So if I'm at equilibrium, then m sub z of 0 does equal m0. Okay, but if I flip 90 degrees, now m sub z of 0 is 0, or if that's time 0. And if I flipped 180 degrees, then m sub 0 of 0 will be minus m sub 0. Okay, if that's my time equals 0. All right, so that's the difference between those two things. So if I apply 90-degree pulse from equilibrium, then the magnetization at this point is all in the transverse plane. So there's nothing in the nothing along the z component. So my m sub 0 of 0 is equal to 0. Okay? So then the recovery is just the exponential recovery from 0, which we talked about last time. It's just this. So it's always recovering to m sub 0. All right? Now, if for inversion recovery, and this is also assuming I'm starting from equilibrium, then I assume I've got m naught here, I tip it 180 degrees, and I have minus m naught. So I'm recovering from minus m naught. All right? So the picture looks like this. Okay? Now this is not the solution you're going to have for your homework because we're not starting from minus m naught. Okay? So that's one thing. You can't just apply this, but this gives you the intuition that wherever I start off from, I'm always going to exponentially recover back to m naught. All right? So let's take a look a bit at the homework problem. So you're given two pulses, a 90-degree pulse and a 180-degree pulse. So you're told immediately after the application of the 90-degree pulse, it should be just pulse, right? The longitudinal magnetization m sub z of 0 is equal to 0. So that makes sense from everything we talked about. I've applied this 90-degree pulse, so there's no m sub z component, right? So we know that after the 90-degree pulse, it's going to recover somewhat, okay? And if m naught, let's say m naught is here, okay, it's going to recover, but we don't know how long it's going to take to recover. Okay, so it may not get fully back to m naught. Okay, so let's say by this time it recovers to some m sub a, some value of m sub a. Okay, which may not be m naught. So in general, we know that m sub a is always going to be less than or equal to m sub naught. All right, so if we don't let it recover very much, m sub a will be very small. If we let it recover for a long time, then m sub a will be m sub naught. Okay, so that's the longitudinal recovery. And then it says, you may assume that the transverse magnetization is 0 when the 180-degree pulse is applied. Okay, so that's all this is saying. At this point here, mxy is equal to 0. Okay, so all we have to do is consider the m sub z component, right? So now that m sub z component is not full m naught, it's only m sub a, right? So then 180-degree pulse flips it, right? So it's going to flip it down to here, right? So it was here, and it flips it down to minus m sub a, and then it's going to recover, okay? And you're trying to get the timing right so that at this point it goes through 0. All right? So this is used quite a lot in everyday practice. This is a form of what's called background suppression pulse. We use that to get rid of some tissues, and so now you are just figuring out the timing of this, okay? If you had done this 30 years ago, this would be your PhD thesis, okay? So there was a PhD thesis that sort of generalized this to many, many pulses, but that's like 30 years ago, all right? So now it's a homework problem. Yes, question.
What does it mean when your total M, I guess your M sub z is 0?
Yeah.
So I guess what's going through, because it's not, never mind.
So the way to think about m sub z being 0 is just basically you have an equal number of spins up and down, sort of on average. So there's no net sort of.
So you kind of measure the time when it gets to that, and then it'll go up to M not anyway over time?
Yeah, so the way this is used is that if at this point, if we actually now applied another 90 degree, this is not part of the problem, but just to answer your question, if we apply another 90-degree pulse and image, okay, then at that point, the thing that's at 0 has 0 magnetization, right? So when we apply 90-degree pulse, it still stays at 0. So it just appears as nothing in our image. So essentially, we wiped out the magnetization from that tissue. So it's a nice way where you can actually go in and erase tissue that you don't want to see. You haven't actually erased it physically, but you've erased the timing is such that it's not going to appear in your image. Yes?
Is it because if you did it at that original time, at that original 90 pulse, you just can't get all the, like, take all the data you can at that level?
You mean at the very first 90-degree pulse? No, the main application is maybe you have like something and it has a lot of fat around the tumor, right? And the fat is making it very hard for you to see what's in that. Or sometimes a lot when there's shoulder injuries, there's like fibrosis and a lot of fat gets intertwined with the muscle. And let's say you really want to just see the muscle and the tendons, you want to get rid of the fat component first. So this is called nulling. So this is a form of what's called nulling.
So you can null different tissues based on their, like, the tissue-specific T2?
Exactly. So in a few lectures, we'll talk about that in more detail, and then, yeah, okay. All right, so that should be, so hopefully help you with that problem. There's still some stuff you have to do on your own, but that's the basic idea that you're trying to figure out that timing of, given some Q value, what is the T2 value? And this is not the T2 relaxation, this is little T2, that's just the notation, all right? Okay. So, and then we talked about how the transverse component decays away with T2. And so what's happening is the magnetization, we tip it, it decays away in the transverse component, and it grows back along the M sub z. So you have to think about these two things happening simultaneously. All right? So we'll revisit this in a few lectures when we talk about image contrast and how to actually manipulate this even more. But that homework problem is sort of your initial introduction to that. All right? So what we want to spend most of the time today on is the gradients and what do the gradients do, and we want to review what they're there for. So remember, the gradients are what allows us to have these spatially varying patterns of the spins, right? And so for every sort of, we apply a gradient, and then at every point in time, we hopefully have imposed upon the spins some spatially varying pattern, where the orientation of the phases of those spins, if we look at it closely, we can tell where we are in k-space. So every point in k-space corresponds to some spatial arrangement of those spins, okay? In a way that's sort of ordered, in a way that that follows that complex exponential. So for example, here, very important point, center of k-space. Kx equals 0, ky equals 0. Right? Most of them will be referenced to the center of k-space because that's where typically you get the biggest signal because that's the average of all your spins. And so that is going to be where there's no variation in the x direction and no variation in the y direction. Okay? So we always want we're always going to be sort of looking at the center of k-space. But obviously we need to acquire other components too because to fill in the details. So for example, this would be somewhere where kx equals 0, there's no variation in the x direction, ky is at some other value. All right. So in this case, let's say the distance between these two spins was 4. Okay, what would ky equal to? Roughly. It'd be roughly 1/4, right? Because we're almost back to pointing in the same direction. Okay? So if this would be roughly 1/4 because we would expect these spins to be like that, right? If we're following along that. Is that right? Yeah. So that's one period. Okay, question.
Is this in the frequency domain, or are we talking about this like in spatial domain?
So that's a good question. So that's the point that is, so this is in the spatial domain. So when we think about the spins, we're always thinking about space. So that's actually physical space. That's actually what's going on in your body. So you can actually imagine all these spins in your body and they're aligned in a certain way, okay? Then, but each spatial pattern corresponds to a point in k-space. Yeah, so this, for example, would be if I were to draw kx, ky, then that spatial pattern would correspond to a point 0, whoops. Okay, this is a little too sensitive. 0, 1/4.
So that is
Because kx equals 0, right, and ky equals 1/4. So basically, every point in k-space corresponds to a spatial pattern over all of space. Okay, so we talked a little bit about this last time. So this is obviously the center of k-space. All the spins are pointing in the same direction. There's no variation in the spins. Okay, and then we can talk about things like here where it's minus 0.25 in kx because the spins going this way are rotating counterclockwise, and they have a period of 4. Okay, so this period is 4. The spins going this way, you can't really tell, but for this example, they're rotating clockwise, and the period is 2. Okay. So in this example, ky equals 0.5 and ky equals minus 0.5 are give you the same answer, just because of how I sampled it. All right. Okay, so then just to remind you what we're doing in Fourier space, the Fourier transform says take some object g of x, y, multiply it by some complex exponential minus j 2 pi kxx plus ky y. Okay? So that is, by applying the gradients, this is what the gradients do. Okay? The gradients actually do that because the multiplication is just implicit. It's how much spin is there, and the gradients are imposing this spatial pattern. All right? And then this integration here is done with the RF coil. That captures all the signal from all the spins. The net magnetization from all the spins is what the coil sees. So that's an integration process. Then we take that number and we put it into the computer, and we say the integration of all those spins tells me the value of this object at this point in k-space. All right? And then we let the gradients run a little longer till we're at some other place in k-space. So now the spatial pattern is different. We still integrate it all, and we take that number and put it in our sort of computer in another, say this is another point in k-space. And then we're going to just fill in all the points in k-space. Right?
So could you say that again? The last bit, after taking the integration with that?
Yeah, so basically we apply the gradient, imposes a spatial pattern. The RF coil sees everything, so it's essentially integrating. Okay, so that signal goes into our amplifier, and then we digitize it, and that put that number into the computer.
Yeah.
The amplitude and phase, actually. We won't get into details right now, but we actually store the real and imaginary numbers. So, you know, it's sort of interesting. Like, in MR is one place where you actually think about real and imaginary numbers all the time, and actually we actually measure them. They're not real imaginary numbers, but that's a very useful concept because the spins are basically phasors, and so we're always looking at where are they along that XY plane, and so thinking about the real and imaginary components is really useful. Basically, it cuts your work down by at least a factor of 2, right? Because otherwise you have to deal with sines and cosines. If you deal with complex exponentials, you can just use e to the j. So things are just much simpler. All right? Yes, question?
So in this slide, the orange dot is basically the lower
The orange dot would be this thing here, right? Because, so how do I know that the orange dot corresponds to the upper integral? Well, that's almost right. It's the spins are not varying. So it's not the kx and ky are not varying. It's the variation along x or along y. In the beginning, it can be sort of confusing going between x and kx, but that's why we sort of talk about it a lot. Okay. Is there a question here? No. Okay, question there? No. Okay. All right. So these are all great questions. And then to remind us, so this is an example that we talked about last time where this is a place where we're at some, if you look at these spins, right, they're sort of aligned in these patterns here, right? So there is some kx, ky value here, right? Okay, so if we were to draw where we are in kx and ky, we're probably out somewhere here. Okay, because if I draw the vector to that, I know that the stripes are perpendicular to that vector, right? But my object is uniform, right? So that spatial pattern of spins is not really a good match for my uniform object. So when I go and add up all those spins and do the vector sum of all those spins, you'll notice all these spins are going to cancel out a lot of these spins, right? Because they're pointing in different directions. And so when I add everything up, I get a relatively small sum, okay? Because it's not a really good fit. So last time we talked about, well, what would be a better fit? So an object that had this sort of spatial pattern would be a better fit for this Fourier component, right? So we can think about cutting out parts of the object, right? So all those spins that were canceling out the other spins, we just cut them out. So we would just remove those spins. So it's like with a bar of chocolate, we just like cut them out and throw them in the trash. Now we have an object that has stripes in it, okay? So now all these spins here can add up constructively. There's nothing to sort of add up destructively, and so now I'm going to get a much bigger value for my Fourier component. Question?
So you get something that's not representative of what you're actually imaging if you take away all the variables?
In this case, it's sort of, this is saying I'm imaging a different object. So there's object 1 and object 2. Just sort of saying if I have two different objects, one object is a better fit for this Fourier component than another object. Okay. So basically, for example, let's say you do this experiment. Let's say I gave you these two objects, right? And I put them in a box so you couldn't see them, right? And I said, you have to tell me which object is which, right? And all you're allowed to do is look at the Fourier transform of it, okay? So in one case, the Fourier transform would have a peak out at that point, right? And so you'd know, so this object 2, you'd expect to have a peak out in that part in Fourier space because it has those stripes in it, whereas object 1 would have its peak mostly at the center of K-space, right? Okay.
Sorry, so you're saying that object 2 naturally its spin system naturally doesn't have those canceling spins in it? Like it has those gaps?
Yeah, so I'm just, so the example is, I mean, you could have, there's lots of different objects in the world, right? So if you have different objects, you're going to have different Fourier transforms, right? So if I if I image like a waffle, like a Belgian waffle, right, that has a lot of patterns in it, it's going to have a different Fourier transform than like a pancake, right? So I'm just saying, you know, these are just two different objects you can have. So if I have like a brain with a tumor and a brain without a tumor, they're going to have different Fourier transforms, right? If they didn't, then this would be really useless, right? Okay, all right. Okay, so the integration of the signal is with the RF coil, and so so the recipe is essentially to do this whole operation, we are multiplying by this phasor pattern. That multiplication is just done implicitly in MR, okay? And then we integrate overall space with the RF coil. So let's look at an example. This is actually a movie of the homework assignment that you're doing. Okay, so this is actually the solution that you should get, or it's very related to it. So this is my object here, right? And this is going to show the phasor pattern. Okay, and we assume it's basically 0 here, 1 here, 0 here, 1 here. So it's an object that just has no spins, some spins, no spins, and some spins. All right. The phasor pattern is, if you have to think about that, that's if there were spins everywhere, what the pattern would be. Okay, so the phasor pattern, the gradients don't know what the object is. So they're just applying these gradient fields. So if there was a spin at that location, it would have a certain phase. Okay. Now in reality, only those spins that exist are going to be present. So this is now my object times my phasor pattern. Okay. And then this is going to be the integration of all that. Okay. And since this is a simulation, it's actually done with just a summation. Whoops. So actually, it's just summing. So in your calculation that you do, you're just summing the spins. Okay. I'm going to play this movie, and what I want you to, we'll play it a few times. Well, actually, I think if I play it, it's too fast. We'll just play it once, and then we'll step through it. Okay. So if you look at the phasor pattern, you notice we're going through different parts in Fourier space. Okay. So we're sort of imposing some spins, some patterns. So if you look at, let me see if I can do it very slowly now. Whoops. Okay, so basically at the center of K-space, when all the spins are fairly aligned, the summation is pretty big. Okay? As I get farther out in K-space, you notice that now the summation is very small. Okay, because I'm at a part in K-space where some of the spins, like all these spins, are pointing one way, and these spins here are pointing the other way, right? So they're canceling each other out. Okay, so then if I look, so basically look at these spins versus these spins, it's a little hard to see on this, but they're canceling each other out. So let's go to a point where whoops, this is the hard part about this thing. So now I'm at a place where now you sort of see the net magnetization is getting bigger again, and you look at the phasor pattern, it's sort of got that up, down variation. So now the pattern of variation of the spins is matching my object. Okay, and then as I go to other places in K-space, that summation stays relatively small because diagonal stripes are not a very good match for my object, and so that's going to be like that. All right. So we're going to set you up for a problem where we're going to give you different objects and you're looking at the vector sum. So for example, here, this is my object. It's just, this is object 1. It's just a 5 by 5 object, and we're at the center of K-space. Yes, go ahead, question.
On the previous slide, I get that that's our kx and ky, like along x and y.
Mm-hmm.
But when we multiply it by the image, what are our axes indicating at this point?
They're still x and y.
They are still x and
Yeah,
y?
this is still an object space.
Okay.
Yeah. This is just the net magnetization. This is now in mx, my. Okay, so that'd be the net magnetization you'd get from that object. Okay. So I'm just going to sit down to draw these a little bit. So this one here is now this object 3 is different. So everywhere there's a blue, that's a -1, and everywhere there's a red, that's 1, and everywhere there's a 0, that's obviously 0. So this is an object that's going from -1 to 1 to -1. So if I'm at the center of K-space, what I do is the spins are all pointing along 1. Okay, the spin have phase of 0, so they're all 1. So I could when I multiply by -1, I get -1. So I get 1, 2, 3, 4, 7 -1s plus 6 plus 1s equals -1. So that's just the vector sum if I took that phasor pattern and multiplied by my object, added it all up. Yes, question?
What am I doing with giving a -1? I get like the 1 is something there. What is a -1?
A -1 just means, so 1 means the magnetization is pointing this way, -1 just means magnetization pointing the other way. So the nice thing about MR is that everything has a very physical interpretation. Okay? So this is the same object, but now I'm multiplying it by another pattern in K-space. So you sort of see this has stripes, this is sort of has this sort of spatial orientation, right? So now if I go through, this one gets multiplied by this. So these are all going to give me -1 still, right? But these phasors these are negative ones, right? So when I multiply them by 1, all these are going to sum up and give me -3. Okay? If I look at these phasors, they're all 1, so I multiply them by -1, they're all going to give me -5. Similarly, this is going to be -3, this is going to be -1. So the sum of all those things is -13. Okay? This is a different object here. Okay, so it's either 1 or 0 in different places. And so I'm going to multiply by this phasor pattern. And so here, you'll notice everywhere I have something, the phasors are pointed along the one direction, right? So I just add up all these, and there's 13 of those. So that just adds up to 13. Okay. So this is obviously not how, I mean, this is very, very simplified version of MR, but essentially, this is for the problem that I'm going to have you guys work on for the next, say, 10 minutes. This is sort of the thinking that I want you to sort of do. So at least you have a chance to practice this, and then on the homeworks there'll be more chances to think about this. Yes, question?
So is our objective, so to speak, objective,
Yes.
is to try and get the biggest vector sum possible when you multiply the object of the phasor?
Well, that might be the objective on a homework assignment. But when we're doing MR, we're going to just be scanning different parts of the K-space. And at different parts in the K-space, the answer is what it is. And then we use that. But you could use that information to, like, let's say someone just showed you the Fourier transform of an object. You could use that to, that's actually a good problem to put on a quiz. If I show you the Fourier transform of an object, you should be able to guess what the object might look like, as long as the peaks are big enough, right? So if I gave you like a Fourier transform where there was some energy here, but there was some energy out there, you would know that that object should have stripes in it. And you should know which angle the stripes are at. Okay? But the fact that it had a lot of energy at that point in K-space, that's just due to what the object had. Okay. Question?
And when you say stripes at an angle, it's just that the tissue or whatever is in that direction is the same and being affected by the gradient the same way.
It means that if, let's say, there was some energy in K-space, it's not necessarily the tissue, just like in the MRI acquisition process, there can be spikes introduced. And so just energy somehow got into K-space at that point. Now, it could be that the tissue was rippled, right? There could be, for example, like along, I'm not sure if it, like along the ribs, let's say. Like if you did, MR is not generally very sensitive to bone, but there are forms of MR that are sensitive to bone. So if you image along the ribs, you should see a pattern. And so you should see something in K-space that tells you that there's this repeating pattern. Okay? All right, so let's move on. I'm going to skip this and come back to this in a minute so we can give you your problem. So I'll open up the poll in a minute, but let me just work you through this problem, and we'll do A together, so you only have to do B, C, D, and E. So this is your object. It's really a very simple object. It's a 5 by 5 object with either 1s and 0s. Okay, so this is the object you put in your MR machine. Now you're trying to be the MR machine and think about what would happen to the object. All right. So for each of these A, B, C, D, and E, I want you to tell me where you are in K-space, and then also what's the vector sum that you get after you take your object and multiply by your phasor pattern. All right. So let's do part A together. So where are we in K-space for A? If you look at the spins, they're all pointing in the same direction, right? So we're at the center of K-space. So that's easy. So we say Kx equals 0, Ky equals 0. Okay? You would have to put for part A for where you are in K-space. Now what's the vector sum of, if I take my object and multiply by my phasor pattern, what's the vector sum? 5, right? So the sum is just equal to 5. All right? So for this one, go ahead and work in groups. Just put your names, and then for each part, you don't have to do A, but for B, put down what the vector sum is. So the answer is not 0. That's just a sample. So put down your vector sum and also where you're in k-space. Make sure when you enter it, you don't hit return after you've entered your name, because then I want the names and the answers all in one line and then enter. Otherwise, I can't tell who responded. Okay? So is that clear? So feel free to get into small groups and discuss if you'd like, and we'll regroup in about 7 minutes. And I'll open up the poll in a minute. You had a question? Oh, okay. So do you have the scores already, or do you want
I have
the
the
mid?
scores,
Okay,
yeah.
so I talked to Professor McVeigh, so we'll turn them back at the
Okay.
end.
Okay, cool.
And yeah.
And I'll upload them tonight.
Okay,
Yeah.
great. Okay, so we're all set on that.
Cool.
Okay.
And then I have an MSTP thing that starts at noon.
Oh yeah, that's fine.
Okay,
Yeah,
cool.
yeah.
Thanks.
Okay, great, super.
Are we not doing it? Are we not doing it? No? Oh.
Yeah, and you can just extend it.
Okay, please submit your answers in the next minute or so. One more minute. Okay, let's regroup and go over the answers. So I think Most people are doing pretty well, but there are some discrepancies, so let's go over it. So for part B, what is the sum of the spins? So we have, this is -1, -1, -1, -1, and this is +1. So the sum is going to be -3, right? Okay. And then where are we in kx? So what's the period? Is there any variation along the x direction? Yeah, and what's the period? 2, right? So we don't know if we went counterclockwise or clockwise, so we might as well just say we're at 1/2. All right? How about along the y direction? Is there any variation? No. So along any column, there's no variation, right? So that's ky equals 0. All right? So let's look at part C. Any questions on part B? Okay. Part C, the sum is what? Still -3, right? Where are we in kx? 0, right? There's no variation along any row. Okay. What about ky? It's there is a period of 2, right? And we can't tell if we're going clockwise or counterclockwise, so we'll just say ky equals 1/2. All right. How about part D? What's the sum here? 5, right? That's pretty easy. Where are we in kx? 1/2, right? And where are we in ky? Also 1/2. Okay, which makes sense. This object has a period of 2 in both directions, so it's got a diagonal pattern, and this pattern of spins also has a diagonal pattern. All right. So therefore, the sum is 5, which is, you know, so the peaks in of this object are both at the center of k space, kx equals 0, ky equals 0, where you get a sum of 5, and also at this other part in k space, 1/2, 1/2, where the pattern now is also a good match for my object. All right. Okay, let's look at part E. What's the sum here? 1, right? Because the plus and minus j's cancel out, right? So I don't force you to include any imaginary numbers in your answer. So the sum is just 1. Where am I in kx? 1/4, right? Because the period is going to be 4. And am I plus 1/4 or minus 1/4? Plus, right? Because along the y direction, I'm going clockwise. Okay, so I know I'm at the plus. What about k sub y? 0, right? Okay. Yes, question.
So we're seeing, or if we see something that has a period of 2, we can't really determine whether it's plus or minus. So that means that normally the Fourier space is just double represented for things that are for kx equals 1/2 and -1/2.
It's basically, yeah, the idea is depending on what your resolution is, there's this uncertainty at the edges of k space. So in fact, you don't actually have to acquire that extra line. And often people don't. So, but if you were going to go to a higher resolution, then they wouldn't be the same. Yeah, because then you could distinguish which way it was going. All right. Okay, any questions? So this is sort of, it's if you understand this problem, that will be good because that's sort of, there will be other problems like this, and this sort of is a very simple way of understanding what's going on with MR. So this is really sort of the fundamentals of MR encoding. All right. So now we're going to transition on into figuring out the MRI signal equation, which is basically what is the MR signal that we measure, and then how do we go through k-space. So we're going to talk about something called k-space trajectories, which is basically how do we cover all these parts in k-space. All right. So just to remind you, the notation we use is this, where we say the BZ field at any location is the sum of the uniform main magnetic field B sub naught plus these gradient fields. Okay, where this is an example of G sub Z, this is an example of G sub Y, and those are basically how the B sub Z component varies in either the X, the Y, or the Z component. For this class, we're going to assume all the gradient fields are linear. I mean, there are forms of MR that use nonlinear gradients, and when we actually do MR, we have to take into account nonlinearities. But for this class, you can assume everything is linear. All right? So we're going to define a g vector with gx I hat plus gy j hat, and so on and so forth, and the typical position vector. Okay? So then all that gxx, gyy, gzz can be written as a dot product of g dot r. All right, so just simplifying our notation so we don't have to carry around that all over until we want to bring it back later. So then we can just say that the BZ field at any space, in point in space, and also we're going to do time, because we're going to vary the gradients with time, is going to equal to B naught plus G of t dot r. Okay, so for now we're going to assume that r doesn't depend on time. Later on we're going to think about moving object, what happens when you image something that's moving. For now we're going to assume it's stationary, so r is not a function of time, but g can be a function of time because we're going to turn the gradients on and off. All right. So just to remind you, you've seen this slide before. One of the things you have to remember about spins and magnetization is it precesses. All right. And in the absence of a gradient, it will precess as follows. It will precess with a frequency omega naught equals gamma b naught. All right. Precess at the Larmor frequency gamma times b naught. Now what we do is we add on these gradients, and so all the gradient says is now the precession frequency at every point in space and time is just gamma times whatever the field is. Okay, and we said the field is that b naught plus that g dot r. So now we have the gamma b naught. So there's a main frequency omega naught, and then there's this delta omega. That's the part we're really going to care about. Okay, so that's that delta omega that we looked at, for example, when we did that exercise with the spins lined up here. It was really only the relative change in frequencies that really mattered. So this is going to be our main focus, this delta omega. Okay, let's work through this. Basically, we want to get an expression for what the phase of every spin is as a function of the gradient history. Okay, so that's our goal. What we can control is the gradients. What we care about is the phase of the spins. So we need some sort of equation that gets us from the gradients to the spin phase. Okay, because it's the spin phase that we want to control and have all those different spatial patterns. Okay, so we know that in general we can write the magnetization at any point in time as the magnetization at time 0 times some complex exponential, which is just its phase, and that phase is going to vary with both space and time. So we know that frequency is just the rate of change of an angle. Okay, so if I have d phi of t, that equals minus omega t. Okay, and the minus is because it's a clockwise progression. All right. So anytime you have phase and frequency, one is just the phase is always, the derivative of the phase is just my frequency. That's the definition of a frequency. So in this case, it's an instantaneous frequency. Okay? The frequency of precession is not always going to be the same because I can turn the gradients on and off. So then I just have to take that equation and integrate it. So now the phase at any given point in time is just the integral of the history of my frequencies. Okay? So that's going to be the integral from 0 of t of omega, and there's that minus sign out there for the clockwise precession. That just turns out to be minus omega naught of t plus this delta phi term, and this is the term we really care about. That's the incremental phase due to the gradients. All right. So then we just plug in. We have delta phi is equal to minus this delta omega, where delta omega is was defined back here. Okay, this is where delta omega was defined, and so we just plug in for that. So that's just gamma g dot r integrated over time. So what we have now is, if I know what the gradients are, okay, in space and time, then I just integrate it, and that will tell me the phase at every point in space and time. All right. So that's what we're going to work up So we're going to go through a bunch of derivations, but the answer actually turns out to be really easy. Okay, so we're just going to go through the derivation just so you see where it comes from, but then we're going to really focus on the answer and how do we use the answer to design MRI pulse sequences. Right. So let's take a look at an example where I turn the gradient on. So let's say this is time equals 0. Okay, and at time equals 0, I turn on the gradient. So the green, that's that green thing. So the gradient goes from 0 and it turns on, and then it turns off at some point. So this is a constant gradient, right? So that means this spin here is going to, if this spin feels this gradient, then it's going to start to precess a little faster than a spin at isocenter. And the rate, this delta phi is just going to be minus gamma gx x times t1. So it's just the integral of that gradient. So if I go to here, over this amount of time, that gamma times gx xt1 gets me maybe 45 degrees, okay? Because it's experienced a frequency that makes it go a little faster for that amount of time. But since it's constant, if I wait another amount of time, then I just integrate over here, and now I'm at 90 degrees. So this is 90, 45, and 135. Okay? So in the presence of a constant gradient, I just constantly accrue phase. Okay? So it's just basically, it's very simple. Right? The cool thing about spins, though, is that they actually have some sort of memory. Okay? So I can actually turn a gradient on, I can turn it off, and I can turn it on again. Okay? And let's see what happens when we do that. So in this case, I turn on this gradient for this amount of time. And so during that amount of time, it's constant. So the spin accrues some phase, right? It's going a little faster, so it accumulates some phase. Then at this point in time here, I turn off the gradient, right? So it's not going to accumulate any more phase. So it just holds its phase at that point. So it's actually storing, it's keeping a memory of its phase, all right? So from here to here, see there's no change in phase. Yeah.
What happens to the relaxation of the return to 0 degrees? I guess my question is,
Yep.
why doesn't it return in the time that it's turned off? Because normally you learn that like the signal comes from, you kind of apply it, it goes 45 minutes and relaxes back.
Yeah. Okay. That's a great question. So we're going to ignore that for now. And the reason we're going to ignore it is we're going to assume we're going so fast that we can ignore it. Now, later on, we're going to talk about how you have to bring that back in.
Okay, so if it's so fast that you can ignore it, then why pretend like you're turning it off in the first place?
Oh, okay. So that's a different question. So the relaxation is, let's say T2 relaxation is 100 milliseconds. So we're going to assume we can do all this stuff in 5 milliseconds, which is actually practical. Okay, so we can actually go through a line of case space in 3 to 5 milliseconds. So that's much less than 100 milliseconds, so we can ignore the T2 relaxation. This is different. This is basically saying that it's going to be advantageous for me to get through case space. I'm going to turn the gradients on and off. Okay, and so I need to understand what happens when I turn a gradient on and off. And so this time scale is, no matter how fast I do that, the spins respond instantaneously, right? They actually can track that change, and no matter, given the fact that we have a limit on how fast we can do the gradients, or even the fastest gradients in the world now, the spins can still track it. So the moment I change the magnetic field, it changes its frequency of precession. Okay, so if I have no added gradient, then it just goes back to the main precession frequency. So there's no added frequency of precession there. Okay, yes, okay. All right, so that's basically, so when I turn off the gradient, it basically remembers its last location in phase. And then I turn the gradient on here, and now it starts accruing phase again. Right? So this is sort of, you can think of this transition here, whoops. This period here is like the spin just remembers what you did to it. And then if you come on later at some other point in time, it just adds on to that memory. All right? Okay, so what happens then is if we put that all together, it turns out that the transverse magnetization at any point in space and time can be written as its initial value times this T2 decay, which we're going to assume for now, we're actually going to ignore this for now, times this phase term. Okay? And we see this phase term can be written as sort of the uniform precession with the omega naught plus this term that has this delta omega in it. And that's what we care about. And that can be written as a function of the gradient. And that's what we can control, so that's what we need to understand how that's going to proceed. And so the gradients are just going to get us a different spatial pattern. So for example, this is one, we start off maybe here at the center of k-space, and if we apply the gradients in the correct manner, then we can get to this part in k-space. And we're just trying to figure out how do we get through k-space. Okay, so remember when we actually do the MR experiment, we actually integrate over the whole volume. Okay, so the RF coil sees the whole volume, so that's the RF coil. And in this case, we're going to expand it out to x, y, z, dx, dy, dz. So we're going to take that term and just sort of integrate everything. Okay. And the simplification we're going to make for now is we're going to focus initially on 2D imaging. Okay, so in MR we can do either 2D or 3D or 4D imaging. So 2D imaging is just we're going to acquire the images slice by slice by slice by slice. Okay, and the cool thing is, and we'll talk about probably next week how we do that, but for now it turns out that by using the gradients in a clever fashion we can excite magnetization only in a slice. Okay, so that way we can just look at what's in a certain slice. All right. So for now we'll assume we can do that. Next week we'll talk about how we do that. But then we can sort of say, then we just really care about what the magnetization is within that slice. So we only care about the XY variation. We assume we've integrated over the Z direction along some slice of thickness delta Z. Okay? So now we're just looking at a 2D image. So if we do that, we can define our signal as the integral of x mxy, this uniform precession term, times this thing that depends on the gradients. Right. The last thing we do is we demodulate the signal. So we multiply by e to the j omega naught t. And we'll talk in a later lecture about how we do that, but that's just done with electronics. So we actually can get rid of that term. And so we're just left with this equation here, which has mxy exponential of some gradient. And that looks very similar to the form of a Fourier transform. Remember, you have an object, you have a complex exponential, and you're integrating it. So now we just work until we get that. We just use some algebra and some definition of variables until we get that into the form of a Fourier transform. So it turns out that now we're going to expand out the g dot r with a gxx and a gyy. Oops. And then we're going to define kx of t equals gamma over 2 pi, the integral of gx of t, and ky of t equals gamma 2 pi integral of gy of t. And if we do that, now we have the Fourier transform of my object. Okay. Where we are in k-space is totally determined by the history of the gradients. And so that's the amazing thing that emerges out of MR is that basically by just controlling the gradients, we can go through k-space, and at every point in time, the signal we measure is just the value of the Fourier transform at that place in k-space. So basically, that's just summarizing here. So the MR signal as a function of time is just the Fourier transform of my object. So just to recap, frequency is the rate of change of phase. With the gradient, we can make spins at different locations spin at different frequencies so that they're going to accumulate phase in different ways. And we're going to use that. That's what allows us to do the Fourier transform. And the main thing that we're going to now focus on is understanding this and how do we manipulate this. So it's basically saying every point in time, we're going to be at some point in k-space. And where we are in k-space, it turns out, the nice thing is the answer is very simple. It's just the integral of the gradient. Okay, so that's all you need to remember. It's just the area under the gradient up to that point in time. So then, even though that's so simple, it turns out that there's many ways of controlling the gradients. And so the name of the game and the subject of many different graduate work and research is how do you control the gradients to go as quickly as possible or to have different properties that are advantageous? Okay, so there's actually thousands, if not, there's definitely thousands, if not tens of thousands of different trajectories that people have come up over the years. Okay, so let's look at the simplest k-space trajectory is I just turn the gradient on and I leave it on. So I start off at the center of k-space, right? Because the area of the gradient up to that point is 0, right? There's been no gradient, so there's nothing on the integral. So I'm at the center of k-space, all the spins are aligned. Okay. And I'm assuming it's a gx gradient, so and assuming this is the x direction, if I let that gradient stay on, the spins are going to get out of alignment in the x direction. Okay. So at time t1, where I'm at k-space is kx of t equals gamma over 2 pi, the integral of that gradient. Okay, so it moves me from here in k-space out to here in k-space. I'm moving along the kx trajectory, kx axis. Okay. Whoops. And then if I leave the gradient on to here at point t2, so this area here drives me to this part in k-space. And then I add some more area on, and now I'm at this point in k-space. So basically, as the area under the gradient increases, it's just moving farther and farther out in kx. All right. So let's talk a little bit about units. So spatial frequencies typically, so they're units of 1 over distance. So for this class, we'll most commonly use 1 over centimeters, although you could also use 1 over millimeters. Gradient strengths are typically in Gauss per centimeters or millitesla per meter. So Gauss per centimeter if you're in the United States and working with a GE machine, millitesla per meter if you have like a Siemens machine, which is from Europe. Okay. And gamma over 2 pi has units of hertz per Gauss or hertz per Tesla. So if we look at this equation, kx of t is gamma over 2 pi times the integral of gx of tau d tau. So that will have units, the correct unit. So I have hertz per Gauss times Gauss per centimeter times seconds. That's 1 over centimeters. So everything checks out. So let's look at an example with actual numbers. Okay, so now I actually have 1 Gauss per centimeter, and I've left this gradient on for 0.235 milliseconds. Okay, and I want to calculate where am I in k-space. So all I have to do is I just take the area of this curve, okay, and multiply by gamma over 2 pi. So I have my 4257 hertz per Gauss times the height times the base, and that gives me 1 inverse centimeters. Okay, so that means if I leave this gradient on for 235 microseconds, that the variation of the spins in the x direction will have a period of 1 centimeter. So here's a k-space trajectory where I turn on the gradient in the gx, and then I turn it off, and then I turn on the gradient in the gy. Okay. So if you notice here, first I turn on the gradient along in gx. So I'm going to move along this trajectory here because I'm accumulating the kx integral is getting bigger. Okay. Then I turn off the gx gradient, so there's no more kx. That kx is not going to get any bigger. I then turn on the gy gradient, so now ky is going to get bigger. So I move in this direction. Okay, so I turn the gradients on, one gradient, I turn it off, and I got out to this point in k-space. Okay, so can anyone think of how I could have gotten out there faster? Yeah, the shortest path would be like this, right? So how would I get there? Just turn on both at the same time. So that's typically what's done. Whenever you can, you have the gradients on at the same time. Okay. Sometimes you can't because for reasons, but in general, you always try to save time and go as quickly as possible to someplace in k-space. So let's look through an example. This is actually, we have my RF pulse here, so that excites. So let's say this is a 90-degree pulse. In this case, I turn on the gy gradient, turn it off, then turn on the gx gradient. And what we're going to do is we're going to look at the spatial pattern of the spins at different points in space, in time. Okay? So at the center of k-space, so at time 1, I'm at the center of k-space. Okay? So all the spins are aligned. So if I integrated that magnetization, I would get that value in k-space. All right. Then I turn on the gy gradient, And now this has some spatial pattern with that period there. Okay, so now the spins are bearing in the y direction. So basically, I've moved out to some point along the ky axis. Right? Then I keep moving out along. I keep that gradient on. So at time point 3, there's even a shorter, smaller period. So I'm farther out in k space. Okay, so now I'm at that orange dot in k space. All right. And then I turn on the gx gradient for some amount of time. So the spatial variation along the y direction stays. Now I just start adding spatial variation along the x direction. And so that's going to give me a diagonal variation. And that's what's shown there. All right. So I've moved up along here in k-space, introducing more and more y variation, and then move this way in k-space, introducing more and more x variation. So now I have x and y variation, which is a diagonal variation. So that's what the gradients have done. All right. So if I want it to be that place in k-space, I need to have both gx and gy gradients played out. So this is a movie that actually just shows you that. So see how we're starting to introduce variation in the y direction, and then at some point we start introducing variation also in the x direction. Okay, question? Yes.
So if we look at plot 2 and 3, is there a way for us to know the frequency just by looking at that pattern?
Sure. So basically you look at this period, right? And so 1 over that period would be your frequency. So this, let's say this period is, let's say this is 10, and this is 5, just for purposes of example. Okay. Then I would know that, for example, this would be 1 over 10, and this would be 1 over 5. All right. Question?
So what is the sort of useful range in k-space if we're looking at repeating frequency, or what the period is in real space? If it repeats every 2 units, then we're talking in k-space it would be a half. If it repeats every 100 units, then it's 0.01.
Yeah. So we'll get to that when we talk about how far out you want to go in k-space, but the answer is it depends on the resolution. Like if you want to see higher resolution, you've got to go farther out in k-space. So if I'm imaging, like if I'm doing microscopic imaging, then I've got to go really far out in k-space.
Per centimeter, I guess.
Yeah.
Yeah.
Yeah. So it really depends. It's a trade-off between your resolution and what's practically doable. So in a human, you can't. The resolution is limited by the fact that the human can only be in there for a certain amount of time. Now, once they're dead, you can take their brain out and stick it in a scanner and scan for a week, and you'll get much better resolution, right? And we'll show you some images of that later on. Yeah. So if you want really high resolution, you just have to make sure it's like a dead object, right? But for in vivo imaging, we are limited because there's just a limit on how long we can scan, and also people can't stay still that long. Okay. Okay. So anyways. That movie is just sort of, this is what the gradients do, and so every point along this k-space trajectory, there's a different spatial pattern of the spins, and at every point in time, we take the integral of all those spins, and that gives us the value of Fourier space. Okay, so this was, we had already talked about that. If I just want to move out to that part in k-space, I just can go directly. And so actually, we have just enough time to do this exercise. Okay, so here's the question. You want to move out in k-space to a location kx equals 1 inverse centimeters to and ky equals 2 inverse centimeters. The time you have is 1 millisecond. Okay, calculate the gradient amplitude that you would need to get out to that part in k-space, and to keep the thing simple, assume that gamma over 2 pi is 4,000 hertz per Gauss, so that the algebra will be very simple. Okay, so your answer should be fairly simple. All right, so we have exactly 7 minutes or 5 minutes to do that. That's plenty of time to do like 2 calculations. All right, and I'll post the slides, the poll very soon.
I did like an experiment, like, and it would last a while. No one told me like what to do, but last like 30, like I basically just went home and just like take a shower and stuff, and then go back with these mice, and it's giving these like film transplants. I had to watch them, or just like another guy in my yeah, I was like, measure stuff.
Okay, go ahead and enter your answers if you haven't already done so. Yeah, question? Oh yeah, okay. If you don't mind staying late. Okay.
Just for this.
Okay, so let's talk about it. Most of the answers are correct, but it's worth talking about it. So remember, kx is going to be equal to gamma over 2 pi times the area of the gradient, right? So we're going to have 1 inverse centimeter equals 4,000 hertz per Gauss, okay? We have 1 times 10 to the minus 3 seconds. And then we're going to solve for g. All right. So g is just going to equal 1 times 10 to the 3 over 4,000 equals 0.25 Gauss per centimeter. All right. And then ky is twice as far out. So given the same amount of time, we just need twice the gradient. So then gy, which is equal 0.5 Gauss per centimeter. All right, any questions on that? Okay, so that's basically showing you that go ahead.
Sorry, so do we always assume that G is a square?
No, but in this case it is a square.
Okay.
Yeah, in reality it can be any shape.
Okay.
But mostly for problems, they'll probably be squares just simply because otherwise, the most complicated we'll ever do in this class is a trapezoid.
Okay.
Which is also easy to get the area of, right?
Sure.
Okay. Great. So let's end there, but let me. I'm going to end this recording, but then let's go and talk about the